Right, now as you've done this derivative, one of the first things we need to do is talk about which method you're going to be using to do it. Because you actually have a number of different options. If you just found the derivative from the form that it's currently in, you can do that. In this case, you'd be using quotient rule. And so low d high minus high d low all over the square of what's below, right? You could go ahead and use quotient rule here, but did you need to use quotient rule? No. You could also have rewritten it in different ways. For instance, you could have written this as x squared plus 4x plus 3 times, let's say, x to the negative 1/2 power. Which rule would we be using if we did it that way? Yep, product rule. So you could do original times derivative plus derivative times original. Or you could have skipped over both of those rules. And if we distribute that in, that would give us x to the 3/2 plus 4x to the 1/2 plus 3x to the negative 1/2, in which case for each term you're just using power rule. And so any of those options would work for this, and it's just really a matter of personal preference about which one you think is going to be easiest or preferable or anything like that as you go. So most did it with quotient rule, so we'll go ahead and do it that way. So then we're going to do low d high, so that means I'm going to do the square root of x times the derivative of my top functions. That's going to be 2x plus 4. Remember, it is then a minus, which is why the order matters here. So minus high d low. So the x squared plus 4x plus 3 stays the same. And in this case, then we multiply that by the derivative of the square root of x. Now notice it's the derivative of root x. It's not the derivative of 1 over root x. It's just the derivative of the square root of x. And so that gives me the, I'm going to go ahead and call it x to the negative 1/2. You could also call it oops, I forgot something there. You could also call it 1 over that. It would actually be 1/2 x to the negative 1/2. And then that's all over the square of what's below. So that would be all over the square root of x squared. And there is, of course, some simplifying we can do along the way here. It all depends on just how deep we want to get into that simplifying process. But like we can distribute in on the top and on the bottom, actually just squaring the square root, that part's going to be easy, right? Because that's just going to make it an x. And so when I distribute in here for doing this, I'm just going to go ahead and write them as fractional exponents for the time being. I can worry about putting them back in a radical form at the end if I want to do that. Notice how I got this 3/2. I did root x times x. And of course that means I'm doing x to the 1/2, that's not a very well written one, times x to the 1, which means adding the exponents. 1/2 plus 1 is the same as 1/2 plus 2 over 2, which is why that's giving us the 3/2 as my new exponent there. All right. Then continuing on from there, we now have the minus. Now, when doing that minus, something good that can help you in doing these is I still keep parentheses there to show that I'm going to distribute, because that negative is going to have to go into everything that I get here. And it's very easy to forget about it if I try to put the negative in while I'm multiplying everything through. So I'm just trying to be very careful there. All right, so it's going to be 1/2 x to the 3/2 plus 4x to the 1/2. Oops, I forgot something with that 4, didn't I? Very easy to make that mistake, because I got to multiply the 4 also by this 1/2 right here. And so then I got to do the same thing with the 3. So 3 times 1/2 gives me 3/2, and then the x to the negative 1/2. And this is all over just x. And we can keep going from there, right? So let's go ahead and go at least one more step. If I combine like terms now, you notice I got a couple of them that are the 3/2. So 2 minus 1/2, that's going to give me 3/2 x to the 3/2. All right, and then I do have a few of them that are x to the 1/2. And so 4x to the 1/2 plus 2x to the 1/2 gives me 6x to the 1/2. Yep, well done, well caught. We're subtracting it, aren't we? So that won't be a 6, that's going to be a 2. Because we have to remember that we are subtracting here. Good. All right, and then the last part, we don't have any like terms with the negative 1/2 power, so that's just going to be minus 3/2 x to the negative 1/2. And it's still all over x. All right, this is pretty good. Obviously, this isn't totally simplified, but if you got even to this point, you're doing pretty well. But if we did want to take it even further, yeah, let's go ahead and clean it up just a little bit more, because that over x thing is just staying out to me is like really easy to simplify, because it is over just x. So that means I can just subtract 1 from each of my exponents that I have up top. So then that would turn into 3/2 x to the 1/2 plus 2 x to the negative 1/2 minus 3/2 x to the negative 3/2. So that's at least a lot cleaner there, because I was able to divide everything through by x. But this still doesn't look very user-friendly, does it? So we could clean it up even a little bit more by putting in some of those radicals and dealing with the negative exponents. So we would end up with 3/2 root x plus 2 over root x minus 3 over 2, and then you have an option here. You either could write it as the square root of x cubed, but since that simplifies down, the square root of x cubed is the same thing as x root x. So I'm going to go ahead and write that as x root x on the bottom there. And if I wanted to, I could go even further past this. I could try to turn it all into a single fraction, or I could try to rationalize denominators. I'm not going to worry about that stuff right now. But just saying some of the things that we can do when it comes to simplifying. Not that we have to do all of these, but just seeing some of those things that we can do to remind ourselves about how we can manipulate these equations. All right, now we end up doing this one with quotient rule because that's what most people used. I'm not going to have you find the derivative of this one, but I'm going to be specific here. We've done this one before, but we've done it using other rules. I'd like you to please actually use quotient rule for this to show how quotient rule is going to give us the same answer as what we were finding before. All right, so let's start plugging it into our quotient rule here. So that's going to be low d high. So that's going to be the bottom function, so that's x, times the derivative of the top function. Now the top function here is 1. What's the derivative of 1? 0, yeah, because it's a constant. All right, then minus high d low. So then that's going to be 1 times the derivative of x. And what's the derivative of x? 1. All right, and then this is all over the square of what's below. So that's going to be all over x squared. All right, and now it's just a matter of doing a little bit of simplifying. Of course, that x times 0 on the top is just going to become 0. So then we end up with a negative 1 on the top over just x squared, which of course we normally write as a negative 1 over x squared. And so you can see that does give us the same thing that we got using power rule. Now, if we had done the work using power rule, we first would have written this out as x to the negative 1. Then we would have turned it into negative 1 times x to the negative 2, and then we would have turned that into negative 1 over x squared. Notice it basically ends up being the same number of steps there, but just seeing that, yeah, both methods work. And I especially want to see this one done because for whatever reason, once we learn a new rule like quotient rule, if I hadn't told you which rule to use for this one, a lot of you would have still used quotient rule. But I also don't want you forgetting that you can use this rule over here as well. So remember all of these different techniques we've been doing, otherwise you might end up forcing it on there. But if you do, I at least want you doing it right. And oftentimes we have a little bit of trouble with that 0 in there. So just be careful with it. All right, more derivative practice. Please find the derivative of this function. All right, so for finding this derivative, do we have to use quotient rule here, or could we use something else? Well, there is one other option that you actually could go with on this. You could have rewritten this as sine of x times x to the negative 1. Did I expect you to do it that way, though? No. I'm guessing that basically everybody would have done this using quotient rule. And so let's go ahead and walk through what that would look like. So then, quotient rule, low d high, so that's going to be x times the derivative of sine of x. What is the derivative of sine? Cosine, positive cosine. All right, then it's quotient rule, so it's a minus. And then it's going to be high d low. So that's going to be just sine of x times the derivative of x, which of course is 1. And then that's all over the square of what's below. So that's going to be all over x squared. Now it's just a matter of cleaning up. So f prime of x is going to equal, well, really we can just do x cosine of x minus sine of x. We can get rid of that 1 up there. And all that's going to be over x squared. And I would say this is actually probably as clean as we can make it. That's a good answer right there. Now, if we had done it using product rule, we'd end up with it written this way in blue. But then we'd just be looking to clean it up. And so if you clean it up by turning it into a single fraction, yes, that actually would still equal the same thing, because I'd have to like multiply top and bottom of this one by x in order to have the x and the x squared in the denominator, which is where this x would come from here. And this minus would show up because of this minus down here. And so we just switch the order of the terms, but yeah, it's the same thing. Now on to the next problem. Again, please find the derivative of this function. All right, and the first thing that we would encounter when doing this is deciding which rule we do want to use. It's certainly set up to be using quotient rule, but the question would be, can you use another rule? Well, in this kind of a case, I could rewrite this as cosine of x times e to the negative x. Do we know what the derivative of e to the negative x is? No, we don't. And that negative being in the exponent actually does change things a little bit. We will be learning in our next section how to do that. That'd be found using something called the chain rule. But since we don't know that yet, we cannot reformat it that way. So we're actually going to have to use the quotient rule in this case. So go for it using the quotient rule. And we should be doing low d high. So that's e to the x, the original on the bottom, times the derivative of the top. Now what's the derivative of cosine? Yep, it's the sine, but the derivative of cosine is the negative sign. So that gives us the negative sign there, minus. And then high d low. So now we're going to do the cosine of x times the derivative of the bottom, but the derivative of e to the x, of course, is e to the x. And then that's all over the square of what's below. So that's going to be all over e to the x squared. Now, certainly I do want to do a little bit of cleanup at least one step's worth of cleanup is well warranted here. And so on the top, both of them end up becoming negative. Yes, you can factor out an e to the x, but oftentimes we like leaving stuff distributed, so I'm going to go ahead and leave it distributed. So I'm going to write it as negative e to the x sine of x minus e to the x cosine of x. And then that's all over, how do I simplify down e to the x squared? Well, we're doing a power to a power, right? Like what if I gave you x squared cubed? What would you do with the 2 and the 3 in that case? You'd multiply them, right? And so that'd give me x to the 6th. Same thing here, where I can multiply my x and my 2. So this is all going to end up becoming e to the power of 2x. And so that would be a nice simplified version, although, wait, I now see something else that I can simplify here. Do you see how this can be simplified further? Nice, because you notice that in both the top and the bottom, in every term, I do have an e to the power of x. So yeah, I could cancel all those out. And so then this whole thing just becomes negative sine x minus cosine of x all over e to the x. Even better. All right, and then that's a great final answer right there. Now please go ahead and find the derivative of this function. All right, so jumping straight in with quotient rule here. This is what we get when we just plug in for quotient rule. But then again, I do want to try to simplify whatever I can here. All right, so I just reordered the top to look a little bit cleaner, but then on the bottom I have sine of x squared. Now remember, sine of x squared can be written, or should be written, as sine squared x like that. So that's how we'd actually write sine squared. All right, now we have a few decisions to make here. For instance, can I simplify it? Well, it's kind of a yes and kind of a no here, because I do see sines here, and I could actually turn this part into cosine over sine squared, which I could turn the cosine over sine part into like cotangent or something. And so technically you can do a little bit of manipulation in that, but I think it's probably going to be a little bit more convoluted than what we're left with right here. So I kind of like leaving it in this form. So I would go ahead and call this good. Now, I jumped straight into using quotient rule here because really we would need quotient rule based on what we've talked about. But we could actually rewrite our original quotient as a product. That would be possible to do. So let's take a look at what that would have looked like. So if I had taken that and rewritten it just as a product, then this would have been 5x cubed times 1 over sine. What does 1 over sine equal? Yep, cosecant. Now, do we know how to find the derivative of cosecant x? No. At least not with that quotient rule and doing a whole bunch of extra work. However, there is a derivative for cosecant of x, and yes, you will know it. In fact, that's one of the things we're going to be doing tomorrow is we're going to see what the derivative of cosecant of x would be. Now, if we had already learned that, then yes, you could rewrite this as a product and do it that way if you wished. But, of course, we don't know that yet, so we wouldn't do it that way. All right, next up. I think you're getting the hang of those. So now let's look at these problems a little bit differently. It's still the same kind of stuff as what we've been doing, but I want to be able to look at finding derivatives where we're already just given some of the values and being able to use those to plug in. So here you have a table that has the f of x values, the g of x values, and both their derivative values at various x's. See if you can use that now to find the derivative of r at 2, where r is defined, notice up here, as f times g. All right, so if we're going to be finding out what r prime of 2 is here, I need to be able to write it all in terms of f and g here. So we're told that r is f times g. So really when we're looking for r prime, what we're trying to figure out is what is f times g prime, which we've actually seen this before, where we saw that that is equal to f g prime plus f prime g. This is in fact part of our notes written just this way, I expect for most of you, because this is product rule. That's why we know that. And so in this particular case then, we just need to get a little bit more specific. So that means I'm going to be looking for the value of f at 2, because of course this is the r prime of 2 value. So I'm going to do f of 2, and that's going to be times g prime, also at 2. Everything here has to be at 2. All right, so then it's going to be plus f prime of 2 times g of 2. You notice all of those are values that we can find in our table. So let's go ahead and do that. So f of 2. So I go down here to the 2 row. In fact, let's just go ahead and highlight that right now. And all I care about is that row, because that's where all of my x values are 2. So I grab the f value, which is negative 2, and I multiply that by the g prime value, which is negative 1. And then it's plus, because of the plus from product rule. And then f prime of 2, I can see that number is 5 in the table. And then g of 2, I can see that number is 0 in the table. So I'm going to end up doing negative 2 times negative 1, which is a positive 2, plus 5 times 0. And 5 times 0, of course, is 0. So the whole thing just equals 2. And we're done. That's what we're looking for with this. It feels a little bit clunky at first when we do these sorts because we're so used to actually having to find the derivatives ourselves and then plug numbers in to find it. We often forget that really what I care about is just what is the value of, for instance, f prime of 2. Do it that way. Well, if it's already given to us, we don't need to find a derivative and recalculate it because it's already been given. So even though these look weirder and look harder, they're actually easier in a lot of ways. So having seen that one done, same table, please now find out what is the value of r prime of 0. Last time it was r prime of 2. Now find r prime of 0. All right, and then when all is said and done, you should have found an answer of negative 6. So now that we've done a couple of them using product rule, yeah, I want to be able to practice this using our other rules as well. So, same table again, so you don't need to recopy the table, same numbers. This time I'd like you to find r prime of 1, but notice that r prime no longer is f times g. Now r prime is defined as f over g. All right, so for this one, we're going to need to be using quotient rule. So, plug into quotient rule at this point. So if I just plug into quotient rule, this is what I'm getting. All right, now it's just a matter of grabbing our values, right? So we're going to do r prime of 1 here. All of these values are 1 as well. So I'm only going to be looking at this row of values where my x's are 1. All right, so then g of 1 is 2. F prime is 0. Oops, no, that was f, sorry. F prime is 3. All right, then minus f of 1 is 0. G prime of 1, not like it's going to matter since it's multiplying by 0, but it is a 1 there. That's all over g of 1, which we found was the 2. So we're going to be doing 2 squared on the bottom. So r prime of 1 equals 6 over 4, which, I mean, we could reduce it. We can call that 3/2, or you could turn it into 1.5, or you could turn it into 1.5, as you wish. Any of those forms would be fine. Now, if we can do it with a table, we can do it with a graph as well, right? So, here's the graph. You're given the definitions of our functions up here. Notice p of x is f times g. Q is f over g. And we have the functions f and g given. Notice f is the top one, g is the bottom one. So, knowing that, please find the derivative of p at 2, and then find the derivative of q at 7. This is the same as what we were just doing with the tables, except you actually have to look at the graph to find the numbers. All right, so for the first one, p, remember, is defined as being f times g. So I'm going to be using product rule there. So for p prime of 2, I first need to figure out what f of 2 is. So I'm always looking at 2 right here. So f, that's the actual y-coordinate there. That's going to be 3, because I'm just looking to see that if I go up and hit the graph there, what height am I at? And then times g prime at 2. So that means the slope of this graph at 2. What's the slope there? That looks like we're going up 1 and over 2, so that's a 1/2. So then plus the derivative of f at 2. And so that means we're looking for what is the slope of that function at that point. Well, notice it's just gone from going down to going up. It's flattened out. And anytime a graph flattens out, what's its slope? 0. And so that's going to be a 0 times our g value there, which is 2. And so then it's just 3 times 1/2, which is 3/2 1.5, 1.5, pick your favorite flavor, and that's all you got to do for that part. All right, next step, we're going to head over and we're going to do the Q one. All right, so for Q, we have to use quotient rule. So Q prime is going to be our low D high minus high D low all over the square of what's below. So that's going to be all over the G prime. Oops, I'm sorry, not G prime, G squared. All right, so then for Q prime at 7. So this time we're only looking at the values at 7. 2, 3, 4, 5, 6, 7 is going to be right here. That's going to be the G value there, which looks to be about 1. So we're going to do 1 times the F prime. So that's the slope of F at that point. Now, thankfully, it is straight at that point. And so we can go ahead and figure out that that's got to be the same as the slope is all the way from here, which is 1/4. So that's going to be 1 times 1/4 minus the F value there. So that's the actual height of that point. So that's going to be 5. And then G prime, that's our slope at this point. Well, it looks like it's going from here down to there. So it looks like we went down 2 and over 3. So that's going to be a slope of a negative 2/3. And that's all over G squared. Remember, we already found that G was 1, so it's going to be over 1 squared. All right, so then that's going to equal 1/4. And actually, over the 1 squared, I don't need to leave room for that. So that's going to be 1/4 minus, actually plus, 10/3. And then we just try to get a common denominator from those. Because yes, it is going to be a little bit nicer to go ahead and clean that up a little bit. So then that would be 3/12 plus 40/12. So if I leave it as an improper fraction, that would be 43/12. Or we could go ahead and turn it into a mixed number. That would be 3 and 7/12. Or you could go into a decimal, which I don't know off the top of my head.